Hello everyone and welcome to today's webinar. My name is Rick Hyde. I'm a client engagement manager at aPriori. I work with many of our customers helping them to define their goals, strategically plan their deployment, and drive sustainable long-term value out of the tool. Prior to joining aPriori, I spent 5 years in the aerospace industry in various engineering and program management roles. I'm pleased to be joined today by Mark Dignam from our product management team, who is responsible for our engineering solutions and electronics cost modules. Mark has played a big role in working with customers and industry experts to define our engineering solutions and the capabilities that you will see today. Today's webinar is scheduled for about an hour. The phone lines will be muted throughout the session. If at any time you have a question, please enter it into the questions window on the right side of your screen. We'll answer as many questions as possible at the end of the session. Any questions not answered during the session will be answered by email shortly after the session has concluded. So today we'll be talking about aPriori's design-to-cost capability and how they enable engineers and product development teams to understand the cost drivers and potential manufacturability issues of the components that they're designing, explore cost trade-offs for design alternatives and different feature sets, and track product costs throughout their life of their product development project. Ultimately, the goal of these three things is reducing late-stage churn, product costs, and time to market. During today's webinar, Mark and I will review the problems we solve and how the solutions work, show you a demo, review 2 short case studies, and wrap up with any questions that there may be. For anybody who's not familiar with aPriori, what we offer is a holistic product cost management solution for our customers. So at our core, we're a simulation company. Our technology allows someone with a limited manufacturing knowledge to import a CAD model, process it through what we call a virtual production environment or a digitally represented factory, and provide the user with not only how or if the part can be manufactured, but also what they might expect to pay for it and where potential opportunities exist to improve it. Our goal is to help organizations better understand and utilize product cost information within their development, sourcing, and manufacturing teams to reduce cost, churn, and ultimately deliver better products to their customers faster. Somewhat tangential to this initial use case, we're also seeing a lot of contract manufacturers and Tier 1 auto suppliers using aPriori to replace their existing quoting solution because of the speed and depth of knowledge that they're able to provide to their OEMs using aPriori. So if we shift gears and dig into what we're going to focus on today, we're really going to look at how our solutions are used by engineering organizations for new product development projects. So if we think about how products are developed, this is somewhat similar to metrics that we see in manufacturing. It's not uncommon to see cost, quality, and delivery metrics. Those translate very well to engineering as well if we swap out quality for meeting functional requirements. So every time an engineer sits down to design something, ultimately they're accountable for these 3 things. So does my product that I'm designing meet the functional requirements that I need it to? Am I on time, and am I launching at my target cost? The interesting thing about these 3 key areas is that they're very closely interrelated. So if I had unlimited time or unlimited resources in one of these domains, it makes the other 2 fairly easy. So an example of that is if I had to meet functional requirements and a target cost, but I didn't have a deadline to meet, it becomes a very easy task to do. The reality is there's always limits on each of these 3 things, so it becomes a balancing act within the engineering organization. And today we're going to talk through really how to meet target costs and the impact that has on the other 2 domains. So if we look at some of the cost-related challenges that we see a lot of our customers facing, it really boils down to, I'll say, a lack of a tool or a lack of visibility. So engineers don't necessarily perhaps know the cost of the product that they're designing. If they do know the cost, perhaps they don't know what those cost drivers are. And that's where our solution, you'll see in the demo, really highlights where those high-cost elements of the design are. Another challenge that we hear from our customers is the inability to efficiently cost trade-offs. So if I'm trying to decide between design 1 or design 2, or perhaps manufacturing regions for a similar design, how do I know if I'm making an impactful change there and what it's doing to the rest of my requirements? So you'll see some of that functionality today. Another thing we're seeing within our customer base is, I'll say, a lack of manufacturing experience or expertise within the engineering organization. And there's probably a couple factors at play there, right? I hear a lot of times the focus of higher education at this point, at least in the engineering world, is not manufacturing. So the new engineers that are coming in and replacing some of the more experienced engineers don't necessarily have that manufacturing experience. Another way we see that loss is via outsourcing. So as more and more of the content within your bill of material is outsourced, companies are losing that core competency for the manufacturing experience around those types of products. Ultimately, to design a high-quality product, you need to understand how it's going to be manufactured and whether or not it can be manufactured. So Mark will dig into that a bit. The results of all of this tends to be late-stage engineering churn. So if we get one of these areas wrong, right? Say we go to market with a product that's too high of a cost or one that's not manufacturable, it generates ECOs and churn within the engineering process, and ultimately delays to potential product launches. And that's what we're trying to address here. So if we talk more specifically about using aPriori for design to cost and our DTC solution, as we call it, we think about some of the questions that we hear a lot within industry and that engineers are asking within these three functional bubbles or domain bubbles that I mentioned earlier. So when we think about the product requirements, right, and evaluating different product designs, what are the costs of doing so? Or what are the costs of manufacturing in the USA versus Mexico versus the Philippines, perhaps? Or do I have the ability to evaluate different material types, and what does that cause the need for me to do in my design requirements? When we think about the schedule, the question becomes, if I'm not reliant on my purchasing team or my suppliers to give me a quote to understand the cost of my product, what does that cut out of my engineering design timeline? If I'm able to do that myself, how much time can I save and how much faster can I release this product? And then on the more obvious front, when we think about target costs, what are the cost drivers in my design? Have I achieved my target cost? And how much have I saved over the course of my project, right? I've done some great work in the engineering design space. What has that resulted in, or how can I track that throughout the process? So when we look at the design to cost solution benefits, it's really addressing those questions within the functional domains that we talked about. So it's the ability to identify and eliminate cost drivers early in the engineering process before anything's been manufactured. So if we can understand those potential manufacturability issues or where we may be driving cost into the product, that gives us the ability to proactively take action on it, right? Whether that's through redesign or whether that's through potentially adding critical dimensions through the manufacturing process to make sure that we have a high quality at the end. It gives us the ability to make those sorts of decisions before we've cut any metal or injected any plastic into a particular part. It also provides us guidance on how to mitigate some of those issues, right? So if we can understand that a potential feature within my design is going to cause manufacturability issues, do I have the opportunity to design that out now before there is a problem? We also have the ability to quickly evaluate alternative designs against each other and understanding based on a cost perspective, but then also overlaying functionality, which one of these designs is the best one and which one do I want to move forward with. We also have standard reports that allow you to not only keep that knowledge to yourself, but disseminate it throughout your organization and make sure that your assumptions are very clearly noted and that everybody understands what the alternatives were and why the selected one was selected. Throughout all of this, we're eliminating surprises, right? We don't get to the end of the design and say, wow, this supplier quotes 30% higher than my target cost. We're able to understand what the target costs are, how we're tracking towards them, both at the component and system level, and reducing risk throughout that engineering process of adding both time delays as well as cost surprises. So with that, I'm actually going to now turn it over to Mark Dignam, and Mark's going to take us through a demo within aPriori showing some of this functionality.
Thanks, Rick. So for my demonstration today, I'm going to be playing the role of an engineer and be going through basically a day in the life of an engineer using aPriori to track and reduce product costs. I'm going to start my day by running a report that gives me visibility into several projects that I have that we're working on within aPriori. So this report will show me data on this particular one on 4 projects that I'm working on. And the data that it's showing me is the target cost that we have set for each one of these projects, shown in the red bars, and the final aPriori cost that we have calculated within aPriori, shown in the light blue bars, and then also the starting point cost that we had in aPriori, shown in the dark blue bars. So this shows us a couple of different critical metrics. First of all, it shows us how we're tracking to our target cost and whether we're above or below that target cost. But it also shows us how much cost we've avoided throughout the design cycle by using aPriori to help optimize our designs. So using this report, I can really quickly see that my engine redesign project is currently over target. I can see it visually on the top, and I can see the actual data on the bottom section where we're showing absolute numbers. So you can see right now I'm over 10% over my target cost for this engine redesign project. So from here, I can dig a little bit more into this project and see the specific components and assemblies that make up this specific project. So this engine redesign project is really simple. It's made up of just a couple of assemblies. We have an engine assembly and a carburetor assembly, both contributing about an equal amount of cost to our total cost of $277. But from my knowledge of these two assemblies, I know that we did a pretty quick job on the carburetor, sort of rushed through the development process and the costing process to try to get something out quickly, and I sense that there's a potential for cost reduction there. So that's where I'm going to focus my time today in the aPriori Professional client. So I'm going to switch over to that, and once I open aPriori Professional, I've already opened up that carburetor assembly. So that's what we're seeing here. And you can see in the bottom left-hand corner we have a 3D representation of this carburetor. So this is taken directly from our Creo model. And in the top panel here we have a breakdown of that assembly. So we can see that it's made up of 5 components here. We have a manifold, we have a carburetor, we have a bolt, actually 5 bolts in this assembly, a carburetor plate, and an air filter cover. And using this assembly breakdown, I can really quickly identify a few things. First of all, I can see my target cost for this carburetor is $100, and my fully burdened cost is currently $141, so I'm pretty significantly over target for this subassembly. And what I can also see is my major cost drivers in terms of components within this assembly. So I can see very quickly that my manifold is by far my biggest cost driver within this assembly. So that's where the biggest potential for cost reduction is, and really where I should start my cost reduction efforts. So that is where I'm going to focus first. So I'm just going to open up this part and start to take a look at its cost drivers and what I can do to reduce the cost. And actually what I'm going to do is create a new scenario. So this is basically a new container for me to explore potential for cost reduction on this component without interfering with the results that I already had. So I'm just going to create that. And that's going to open very quickly for me now. So now I have that place for me to do some explorations. As I get started on these explorations, let me just give you a quick introduction in terms of how we develop a cost in aPriori and the data that we're outputting. So obviously for this manifold, we've already costed it since we had a fully burdened cost of just over $84. And the way that we costed it was by just providing 5 simple inputs up front. So those inputs are contained on the left-hand side of our screen here and in the cost guide. So the cost guide is an interface that walks us through the inputs that we need to provide to develop a cost. So the inputs that I provided were simply the process group. So this is a high-level categorization of how this part will be manufactured. Is it going to be a sheet metal part? Is it a rapid prototyping part? Is it a stock machine part? Very high-level categorization that most users that will be interacting with a component should absolutely know about their component. The next input that I provided was what virtual production environment, or VPE, this is going to be manufactured in. So which digital factory are we going to use to calculate this cost and determine whether or not individual features are manufacturable. So I've selected aPriori USA. We have many options available out of the box, and these regions can also be configured for specific customer needs. The next input that I provided was simply my material, which I've chosen an aluminum 6061. This material can be selected directly within aPriori. We ship with many materials out of the box. We can also pull these materials directly from your CAD model. So if materials are specified in the model itself, we can pull that data directly into aPriori and select the material based on that data that's on the model itself. The last set of inputs that I needed to provide to develop this cost were just the production volume information. So how many of these are we going to make per year? How many years are we going to make this for? And if known, how many are we going to make per batch? So this helps us make various determinations in terms of which processes are feasible and also how we should amortize the various setup costs and investment costs that are associated with a component. So those are the set of inputs that I provided to develop this cost. From those inputs and from the data that we pull from the CAD model itself, we generate a very detailed cost breakdown. We're not going to get into all the details that we output today, just going to focus on the outputs that are really targeted towards an engineer. So the first screen that we see and that we really interact with as an engineer is this part summary tab. So this is this upper right-hand panel that we're looking at now. And this tab gives us a high-level view of what this component is and also what its costs are. So we can see the physical information about this component in the upper left-hand corner in terms of its size and its weight. We can see our basic production inputs here in the upper middle panel just to give us a sense of exactly what our assumptions were. And then we can see in the upper right-hand corner what our material assumptions were as well in terms of the actual material type, the stock size that we used, and also the unit cost that we assumed for that material. Now in the bottom portion of this view, we start to get into the cost outputs and start to get into data that's going to help us understand where we should be focusing our efforts for cost reduction. This cost by category panel, basically what this is showing us is a high-level cost breakdown that helps us understand, is most of our costs coming from material? Is it coming from labor and overhead? Is it coming from our investment costs? And from looking at this breakdown, I can see really quickly that my material cost is a very, very small cost driver, making up 1% of my overall cost, whereas labor and overhead are significant cost drivers, making up over 70% of my cost. So what that's telling me is I should really focus my efforts on reducing the amount of manufacturing processing that's required for this part, and I don't really need to spend much time on investigating new materials because that's such a small contributor to my overall cost. So with that information, I move over to my cost by process breakdown, which provides me a little bit more detailed information about where those manufacturing costs are actually falling. So this gives me a breakdown of the manufacturing processes that are being applied to my part. So I can see we require a bandsaw, a 3-axis mill, and a cylindrical grinder. And it also gives me a breakdown of how those processes are contributing to costs. So I can see that my cylindrical grinder is by far my biggest cost driver here, making up almost 60% of my manufacturing costs. So that's a flag for me that I should really be looking at how to reduce that cylindrical grinder process because it is such a big cost driver. And we can actually see the specific features that are being manufactured using that cylindrical grinder by just clicking on that row, and we can see those features highlighted in the model. So that's very useful information to help guide me in terms of where I should be focusing my efforts. And as an engineer, the next step I'm going to take is looking at our design to cost view. So this is going to give me a little bit more guided information in terms of how I should be removing those processes and be reducing my product cost. So this design to cost view is really designed explicitly for engineers to help serve up information that they can understand. So we try to simplify manufacturing information to make it more clear in terms of what these manufacturing processes are and what the assumptions are. And we also targeted it to be actionable by engineers. So we focused it on things that they control today. So things like material selection, geometry of their part, tolerances that are applied to their part. So I'm going to give you a tour of this screen that we have for stock machine components. We also have a view available for plastics. And in the end of the summer of this year, we'll have additional views for casting components, for sheet metal components as well. So the way that we've designed this view is we've broken it down into 2 sub-tabs. The first one is a validation tab that exposes the critical assumptions that we've made within our calculations that impact the rest of the outputs that we generate. So these are really, really high-level assumptions that 95% of the time we get correct, but if they're incorrect, their impact is so significant that we just want to make sure that users take the time to validate that they are accurate. So those assumptions that we're exposing are things like the stock form that we're assuming that this component is made out of. So we can see for this part, it's made out of a rectangular bar, which based on the geometry of this part looks correct. Now, if aPriori were telling us that we assumed that this was made out of a round tube, that would be a flag for me that some assumption was incorrect. And I could resolve that issue by just clicking on the action button here, which would launch our stock form selection tool and allow me to override that assumption. Now, just to give you some insight into the other metrics that we're exposing here, we're also exposing the manufacturing routing, which for machining makes a significant difference if you're manufacturing on a 3-axis mill, a 4-axis mill, or 5-axis mill. Those are very different processes with very different assumptions and very different capabilities. So we just want to make sure that that is confirmed. And then also things like the number of setups for milling and for turning are also critical machining assumptions that really need to be validated before moving on to acting on the outputs. Now, it's understood that a lot of engineers may not know exactly what these assumptions are, but these are really flags for them to, if they don't know if these are the correct assumptions, to contact the manufacturing or a cost expert to confirm that the assumptions are accurate. Now, once we have those validation metrics confirmed, we can move on to our design to cost information tab, where this is where we're showing the real actionable information to engineers. And the way that we've broken this tab down is we've organized it into actionable panels that really have a common theme amongst the panel. And within each one of these panels, we have a little bit of help that explains exactly what the metrics that we're exposing are, and what they represent, and when engineers should be taking action on them. So for this first panel that we have, machining issues represents potential manufacturability issues within my component. So anytime this value is greater than 0, I really need to dive into the review issues to see exactly what those issues are. And within this dialog, I can see various categories of potential machining issues. For this part, I only have sharp corners, and you can see that I have 15 sharp corners, which when I click on that, it will highlight the GCDs that represent exactly where this issue lies. And then in the bottom of this dialog, I get some basic guidance that tells me some way what this issue is. So a sharp corner is something that would require a tool with no diameter to manufacture. And then it also gives me some paths to resolution. So I can override some of the manufacturing assumptions, or if the sharp corner was unintentional, I can go into my CAD model and update the geometry to make this geometry more manufacturable. Now, we also have more detailed explanations in terms of what this issue is and how to resolve it within the help dialog within the machining issues. So this gives me a visual guide in terms of how I should actually resolve this issue. So on the left-hand corner, we can see what this manufacturing issue actually is. So with a sharp corner, you can't get that cylindrical tool in there to actually manufacture that geometry. And to resolve that, we simply need to add a fillet to those corners to make sure that it can be manufactured with a cylindrical tool. So this, just looking at my part, was simply an oversight in my design. Like I said, we did this design very, very quickly. So this is a change that I can make in my CAD model relatively quickly, which I'll do right now, and then we can go back to aPriori to see our results. So I'm just going to find those 3 sharp corners that I had. I'm going to add a 5mm round to them, and I'm going to save my model and come back in aPriori and kick off a recosting. So basically what's happening now is we're looking at that updated CAD model. We're going to extract the new geometry, and then we're going to go through our whole costing engine where we figure out whether or not each individual feature can be made, how long it's going to take to make that feature based on our manufacturing assumptions that we have in our VPE, and then we're going to roll up all those times to calculate an overall cycle time for the part and apply our labor and overhead rates for each individual manufacturing process to calculate a cost. And once this is done, we should see the geometry update in our viewer, which we can see here. You can see that I now have fillets in those corners that were highlighted before. And if I look in my design to cost tab, I can see my machining issues is now down to 0. So I've resolved those sharp corner issues that I had before, and I can now move on to the rest of the information in my design to cost tab. Now, I'm going to go through some of these panels rather quickly, such as the material panel, since, as you remember from the part summary tab, material was a very, very small cost driver for this part. So there's not a lot of action for me to take here, but just for some insight into what we're exposing here, what we're showing here is both the material that you're currently using on your part, but also the cost per volume of this material relative to the rest of the materials that you have available within your virtual production environment. So we can see that this material is currently a little bit higher than the average material cost that we have within our virtual production environment. So there is some potential for me to reduce my material cost, but like I said, since it's such a small cost driver, it's really not worth the effort to go through the investigation of whether or not this material actually meets my functional needs. But if I wanted to actually select a different material, I could select it from directly within this design to cost view, where we can bring up our material selection. We can view them by material type. We can view across all material types and make an informed decision using the data that's available here. The next panel that we have, again, is focused on material and specifically on material utilization and whether or not your material is a custom, whether or not your stock is a custom size. So custom stocks are pretty expensive to manufacture and should be avoided whenever possible. So whenever you see a custom stock size as yes, that's a call that I should be taking some action to try to find a different stock size. And we can do that by launching our review stocks dialog, which allows us to see what our stock assumption is. So you can see the stock assumption in red and the part outline in yellow. So we're adding a little bit of allowance on the top and the bottom of this part to allow those faces to be machined. But we are using a standard stock size, so that's we're okay with that assumption. The next panel that we have is focused on tolerances. So tolerances can be a really, really big cost driver in part, since they can cause expensive operations like cylindrical grinding to be applied to your part to achieve those tolerances. So what we're exposing here are two key metrics. The first one is the number of features that actually have tolerances. This is a check for me to understand whether or not my scenario in aPriori has been fully toleranced, but also the number of features that have specialized finishing based on tolerances. So the fact that I have 16 features on this part that require specialized finishing is a call that I should really be reviewing what those assumptions are and diving into the review tolerances dialog. So from within here, I can see the specific features that are requiring specialized finishing. So I have 4 features that require reaming, and I have 12 features that require general grinding. But what's really useful and really actionable from within this dialog is for each individual feature, I can see what tolerances were applied. So on this curved wall, I have a 200th millimeter diametric tolerance. And then the actionable information that we have here is we show the best achievable tolerance, this is the tolerance that I have to back off to remove this specialized finishing operation. So if I back my tolerance off to 0.0381 millimeters, I will remove the need for that general grinding. So this is really definitive information for me to go back and decide, okay, can I back this tolerance off to 0.0381 millimeters and still meet my functional requirements? And if I do that, I will reduce my product cost. So these would be changes that I would need to make in my CAD model that would take me a little bit longer than adding those rounds. So I've done them already and costed a scenario already in aPriori, and let me just bring up those results. So this is our model with updated tolerances. As you can see, I now only have 4 features with specialized finishing, since those curved walls that had the tight tolerances really are not driving the functionality of this manifold. So I've made a good reduction in the number of features that require specialized finishing, and if I just check that dialog, it's still those 4 reamed holes, which really the diameter of those holes is really critical to the functionality of my part, so I'm okay with them having that specialized finishing. So just in the interest of time, I'm going to skip over our setups panel and just focus on our second to last panel here, which is our holes and fillets. So what we're exposing here is the number of distinct hole diameters that exist in your part and the number of distinct indirect fillet radiuses that exist in your part. And the reason why these are important metrics for us to expose and for engineers to understand is because the more unique hole diameters and the more unique fillet radii that you have in a part, the higher the number of tools that you're going to require to manufacture your part is, and therefore it's going to be more complex to manufacture, more costly to manufacture. So you want to minimize the number of hole diameters and fillet radiuses that you actually use, which in my case with 2 hole diameters and 1 fillet radius, that's a pretty good design. I can view which individual features require which hole diameters or which tool diameters in my part. So I can see that I have a couple of holes that require a 5mm tool to make and a couple of holes that require a 6mm tool to make. These could potentially be consolidated into one hole diameter, but that'd be a decision that I need to think about a little bit more in terms of the load that these individual bolts are holding and just the functional requirements on my part. So I'm not going to take any action here, but it's just some insight into what we're exposing. And then the last panel that we have here is just exposing slow, expensive machining operations. So contouring is a very slow, very expensive machining operation that should only really be used when absolutely necessary. So if you have a specific shape that's required to meet the functionality of your part, then that requires contouring. That is understandable, but whenever possible, it should be avoided. So within this dialog, I can view the specific features that require contouring, which on my part, it just so happens that all these features are part of the interior of the manifold, which is pretty much the most critical part of this manifold's functionality. So I'm okay with the fact that these are requiring contouring, but I am armed with the information that each one of these spaces is requiring a fairly significant amount of cycle time, but it just helps me understand what those cost drivers are and helps me understand the impact of having that geometry. So no action to take on this screen, but it's good for me to understand the impact of my design decision. So that takes us all the way through all the metrics that we're exposing within this design to cost tab for stock machining. And I've made some pretty good progress on this part. So now if I want to see the impact of that progress, I want to see how much I've actually reduced my cost for this component, I can just look at our cost summary tab, which allows us to view a sort of economic breakdown of this component. And I can see that my fully burdened cost is now $21. And if I want to see these results side by side next to each other, I can do that within a comparison. So this is similar to an e-commerce type comparison where when you're comparing TVs or refrigerators or whatever you want to buy on Best Buy, I can view the results side by side. So I've added the 3 scenarios that we've worked on today to this comparison, and I can see on the very left-hand side my starting point with my fully burdened cost of just over $84, and I can see my second scenario is the one where we updated our tolerances. So we can see that significant cost reduction, over 75% of our cost was reduced from this component just by walking through that design to cost tab and the guidance that was provided. So what we can also see in here is that middle scenario that I created where I removed those sharp corners but did not update my tolerances, which still resulted in a pretty significant cost reduction. So this is good information for me to go to the rest of my team and say, hey, if we update this design to remove these manufacturability issues, I'm going to reduce our cost a pretty good amount, but if we remove these tight tolerances on these curved walls, we're going to significantly reduce our product cost. I can bring that information in the form of just showing them my screen here, but what I can also do is aPriori has several spreadsheet reports available that can be run at any time by any user. So we have a cost comparison report, which I'll run right now, and this will just export the basic information that we see in this view to an Excel format that could then be printed or emailed to the key stakeholders in the decision making for the manifold and the key members of my team. So you can see the data that we export here, the high level information in terms of what this component is, where it's being made, and we're also exporting the cost breakdown that we saw in aPriori. That was a full tour of sort of how we would work from understanding how our overall project is tracking relative to our target cost and working our way all the way down to investigating an individual component. With that, I'm going to pass it back to Rick Hyde, who's going to walk through a couple of customer examples.
Excellent. Thanks, Mark. So these couple of examples came from presentations by our customers at our Cost Insight Conference, which is our customer conference that we held this past February. So we had a great attendance there, a number of very successful customers, but we're going to look at just 2 of them right now. So the first one we're going to hear from is Spirit AeroSystems and their manager of cost estimation, David McGinley.
A couple of quick results to date. So the first example here is one. This is probably one of our first items we identified. Was we ran this part through the tool, and immediately several things popped up on here that just got our attention. There was some external radii being put into this part. There was some filleting being done around the periphery of the part, and the values of those radiuses were all the same. So, and then there was some contouring going on. So when you looked at the whole part and you started looking at all these features, they jumped out at you as in the design to cost, the drivers. And so we started asking, questions of the designers. It's like, okay, are these requirements? What are we doing here? What are we trying to achieve here? And really, in this case, it was a pretty young, inexperienced designer. He really hadn't considered how this part might be made. He didn't really think about what the cutter paths would be or how the cutters would be engaged in the part. Or even, in the case of a simple edge radius in CATIA, you can do things so easily, you tend to just do things, and you may not think about what that cost impact was. So as we went through that, engaged in dialogue about, requirements versus what looks nice and all this stuff, they came back with a revised model where they removed the radiuses and changed the fillets so it would accommodate a better cutter path, changed the contouring to some planar surfaces, and I think actually those paths are even gone today. There was some further discussion that took place about were they even necessary at all. And with all those changes, in this case, the opportunity was to reduce that cost by about 11% for this part for a very minimal weight change, almost negligible weight change. And so, that's, we saw this as pretty much a win-win. It's like, we met all the requirements, and we have an opportunity to reduce the cost here. And the designer can quantify those costs. That's another key thing for engineering, to be able to quantify a cost of a part, whether we believe it's the should cost value or accurate, it still gives us an idea of where that part cost is going to be. So that's pretty valuable.
So some great feedback from Spirit there, right? The ability to fairly quickly reduce their part cost by 11% without impacting any of the other parameters, just by understanding the data that aPriori is providing and having a conversation around that. So the next example we have is from Wucheng, and we're going to hear about what they were able to accomplish using aPriori.
Here we're going from a lot of pieces that were bar stock and a big stamping plate, a lot of welding, and moving that to two pieces with stage tooling. To realize a 25% cost savings, this is achieving the same maximum stress level, so we expect the reliability to be the same, saving 3 kilograms of weight. On the right is another bracket, which was composed of a tube and 2 plates that were cut with a blanking die. And then we were able to analyze that and also design a progressive die part. So the volume on this part is something around 800,000 per year, so saving 15% cost, and that's actually a quote we have from the supplier. So in total, this is well above $1 million of savings just in the brackets I presented here.
So again, just to recap, some fairly, I'll say, simple parts that they were looking at, but by looking at the manufacturing methodology and getting some modest cost savings due to the high volumes that Wucheng runs, they were able to save over $1 million fairly quickly and take that directly to their bottom line. So those are just 2 examples. As you can see on this chart, we work with a number of global enterprise organizations, and we continue to show progress at each of these customers. So with that, I hope everybody has a good day. I appreciate the attentiveness. Again, if anybody has additional questions, please reach out to Peyton and we'll make sure we get those answered for you. So this will conclude the webinar. We'll talk to you guys soon.